Thank you very much. And thanks to the organizers first for organizing this wonderful conference and also for giving me the opportunity to give this talk. This is about a joint project with Sergio Giron-Pacheco from who's currently at KU Leuven, and Masaki Izumi from Kyoto. And it's about topological invariants for G-kernels and group actions. Also a bit of a work in progress, but I like it, so I will talk about it anyway. Okay, so I will start in the same way that, oops, the pointer is also not working, so maybe I'll just use the keyboard. Right, so I will start at the same point that Jacek also started. I will look at actions of groups on C-star algebras. So the setting that I will consider are countable discrete groups. A will be a unital, most of the time separable C-star algebra. And then I will consider an action. So what's an action? It's just a homomorphism from G to the automorphisms of A, star automorphisms of A. And then there are several notions that are related to that, and one of them is the notion of a G-kernel. These are sometimes also called anomalous actions. And a G-kernel is just a group homomorphism from G, but not to the automorphism group, but to the group of outer automorphisms, which is the quotient of the automorphism group by the inner ones. And maybe for this crowd, it's important to point out this is an O, it's not a Q. Right, so that's a G-kernel, and there's a second related notion, and that's one of a co-cycle action. So what's that? A co-cycle action is a pair consisting of a map from G to the automorphism group alpha, and alpha is not a group homomorphism, it is a group homomorphism up to conjugation by a unitary, right? So you have this unitary map from G times G to U of A, and U measures how far away alpha is from being a homomorphism. And then there's a second condition that the U has to satisfy, which is this one here, which looks a bit mysterious at first, but it's very natural. This comes from looking at the associativity constraint here. So if you here look at associativity, you want these two sides to be equal. If you plug in what this is using the first relation, then you get the left-hand side and the right-hand side for each of these inside the AT. And for a co-cycle action, you demand that this holds on the nose and not just inside the adjoint action. And now you can, of course, try to relate the two. So one thing that you can do is you can start with the G-kernel, so homomorphism from G to the outer automorphisms, and try to lift it, right? And one thing that always works is you can lift the alpha bar to a map from G to the automorphisms. And because the alpha bar is a group homomorphism, you can also find unitaries such that this line here holds, right? So, and then the thing that goes wrong is exactly this second condition, this associativity constraint. This doesn't have to hold on the nose, of course. But it has to hold up to some element omega, which will depend on the three group elements involved, omega, G, H, K. This will be an element of the center of the unitary group, and that condition here holds. And it turns out that this omega is in fact a group co-cycle. So you get an element, you get a co-cycle, a free co-cycle on the group G with values in the center of the unitary group, which then of course represents a group cohomology class. And it turns out that this group cohomology class does not depend on your choice of unitaries, and it vanishes if and only if the alpha bar lifts to a co-cycle action. So that's all very nice. Still, you might wonder, why should I ever look at these G-kernels? Well, one reason is because they have been incredibly successful when dealing with group actions on von Neumann algebras, because there's this very beautiful result that was proven by Kohn, Jones, and Ogneanu. So Kohn proved this first for cyclic group actions. Jones extended this to finite group actions, and Ogneanu then to amenable group actions. And the result is, in these three cases, that the obstruction that you get this co-cycle is actually a complete invariant for injective G-kernels up to conjugacy. Right, so that's amazing. And then there's also this realization result, namely that for every group cohomology class, there is actually an injective G-kernel, such that it is the obstruction to lifting. So all the classes are realized, and they give a complete invariant up to conjugacy. And now, of course, one thing that you might want to do is you might want to find out are these statements, are statements like this still true for C-star algebras instead of for Neumann algebras? And maybe a good starting point here is you can look at C-star algebras that are kind of the analog of this hyperfinite 2-1 factor from the classification program. And one algebra that pops up there is the so-called Jiangsu algebra. And it is a tracial C-star algebra. It's a stably finite C-star algebra. It has also a nice property that's called strongly self-absorbing. So if I take Z, which is the name for this Jiangsu algebra, tensor it with itself, the result will be isomorphic to the Jiangsu algebra again in a very nice way. So if you look at G-kernels on the Jiangsu algebra, then you find out that things are more difficult now, because if I have a G-kernel on this Jiangsu algebra, then it turns out the obstruction to lifting will just be 0, always. And so that's bad if you want like a realization result like the second one that immediately goes wrong. There's a second C-star algebra that you could look at that also comes up and is related to the hyperfinite 2-1 factor. You could also just take the infinite tensor product of matrix algebras. And if you do that, then you can look at G-kernels on this, but it turns out that you have also restrictions there, namely the order of this obstruction class is somehow, there are strong restrictions on that coming from this supernatural number that classifies this UHF algebra that you have there. Right, and these are results by Sam Eddington and Sergio Giron Pacheco.
So for the Jiangsu algebras, it's for finite groups?
Sorry?
The first theorem is for finite groups?
I think this was for all groups. This was quite general. The second one is for finite groups. Yeah, I should have said it. Right, okay, so for C-star algebras, you have to be more clever. You have to come up with new invariants. And one invariant is one that Izumi looked at. And for this, you make the following assumptions. You take A to be a unital C-star algebra, and you want the unitary group to be path connected. You want the center of the unitary group to be just the circle group T. And then there's a natural map from pi1 from the fundamental group of the unitary group to the K0 group of the C-star algebra. You want that to be an isomorphism. There are several examples from the classification program that satisfy these conditions. For example, the Jiangsu algebra does. The Kunz algebras that we've seen before in previous talks also do, including the algebra O infinity. The UHF algebra, so these infinite tensor products of matrix algebras also work, and UHF algebra tensor O infinity would be another example. And when you have these conditions, then you can look at a modification of the K0 group, defined as follows. So what you do is you look at paths gamma into the unitary group that start at the identity and end up in the center, so in the circle. And then you mod out by the path component of the identity. So S of A is the suspension of A. So these are the loops at the identity. You take the unitary loops at the identity. You take the identity component of that. That's what you mod out by. And then it turns out that this group fits into a short exact sequence. I can just evaluate my path at 1, and I get an element of the circle. And the kernel of that, because of our assumption about the fundamental group, will just be K0 of A. Right. And then, so this is where the invariant will live. And then what I can do is I can play the same game as before. So I start with the G-kernel, I lift it to a map to the automorphism group, I have my unitaries, but then I also extend my unitaries to paths that start at the identity and end at this unitary element that I've picked. And then I can use the paths instead of the unitaries themselves and get an element like this, which I mean, you should now by now recognize that this is like the left-hand side of the thing that we've seen before. This is the right-hand side inverse. So this will be an element that lives in this group K0 hash of A that I've defined before. And the whole thing will again be a co-cycle, representing a class in here. Okay, so that's a new invariant. So we've at least now seen two invariants for these G-kernels on C-star algebra. So the question is, can we somehow put them into some unifying framework that captures what's going on here, right? Because we're always doing the same thing here. So there should be something there. And there is, and to explain what's going on, I need to introduce an algebraic notion, an algebraic topological notion, namely that of a crossed module. So a crossed module is a triple like this. You have two topological groups, gamma 0 and gamma 1, and a continuous group homomorphism from gamma 1 to gamma 0. And then there's a thing that I never write down, but it's there. So I have a left action of gamma 0 on gamma 1, so I will denote the elements in gamma 0 suggestively by alphas. The elements in gamma 1 will be u's and v's. And then I have the following two conditions. The first one says that this delta that I have intertwines the left action of gamma 0 on gamma 1 with the conjugation action in gamma 0, right? That's what this says. And then there's another thing that I can do is I can take an element in gamma 1, map it first to gamma 0, and then act with it, and that should also be equal to the conjugation. So these are the two conditions. I think they're sometimes called Pfeiffer rules. Then you might wonder, are there any examples of this? So one thing that I can do is I can take for gamma 0 just the trivial group, and then you can see from the second condition here that this forces your gamma 1 actually to be abelian, and that actually works, right? So if I pick an abelian group for gamma 1 and gamma 0 the trivial group, this will give me a crossed module. I can also swap the roles, but then I'm allowed to, so I can choose gamma 0 to be an arbitrary topological group, and gamma 1 to be trivial. That will also be a crossed module. And then I can slightly modify this. I can pick for gamma 1 a normal subgroup of gamma 0, and the action of gamma 0 on gamma 1 by conjugation will give me another crossed module. Right. So what is the deal with crossed modules? One thing that I can do is I can now define one co-cycles on my group with values in the cross module. And so what's a one co-cycle? Well, a one co-cycle is a pair, alpha and u, where alpha is a map to gamma 0, u is a map to gamma 1, and they satisfy the following conditions, and you recognize these from before. And there is a notion of, so there's an equivalence relation on this. Don't worry about this too much. So there's an equivalence relation defined like this, which tells me when two of these co-cycles are cohomologous. And then I can take the quotient and call this the first cohomology of G with coefficients in the cross module. There's a major caveat at this point, namely, without any further assumptions on the cross module, these quotients here will just be sets. They will just be pointed sets. And so in general, you don't get a group structure. You just have this. And we will see why that is, I mean, not surprising in maybe a few minutes. Okay, so that's cohomology with coefficients in the cross module. How does this relate to the things that I was telling you about before? There are several examples of cross modules that you can associate naturally to C-star algebras. So the first one is the most canonical one, where I pick for gamma 0 the automorphism group of my C-star algebra. For gamma 1, I pick the unitary group. Then I need a map from the unitary group to the automorphism group. That's easy. I can just pick the adjoint action. And that gives the whole thing the structure of a cross module. The action of the automorphism group on the unitary group is, of course, the canonical one. And then if you sit down and write down what co-cycles are for on G, one co-cycles on G with coefficients in this cross module, these are exactly the co-cycle actions on a up to co-cycle conjugacy. And then I can start modifying this example to get everything I had before. So one thing I can do is I can take the unitary group, mod out by the center, and get what I will denote by the projective unitary group. And then everything else stays the same, and everything still works. I get another cross module from this. And if I now sit down and write down what the co-cycles are, remember then that when I try to lift the G-kernel to a co-cycle action, my only choice were these elements in the center. And I've now taken those away. So you can see that now the co-cycles are in one-to-one correspondence exactly with the G-kernels up to conjugacy. All right, there's another example that works if the unitary group is connected. Then I can take its universal cover, which is another topological group. And then for the adjoint action, I can first project down from the universal cover to the group itself and then act by the adjoint action. And that gives me another cross module. So there's a little bit of checking that you need to do there, but it still works. So that's another one. All right, so how do the lifting obstructions and these Izumi invariant that I spoke about before, how do these come in? Well, I can now look at exact sequences of these cross modules. Right, so here's one. I take the one that I get from the projective unitary group, the one that I get from the unitary group, and then in the kernel of that, I have the center sitting over the trivial group. That's another cross module. So this is a short exact sequence of cross modules. And it turns out that such a short exact sequence of cross modules wants to give rise to a long exact sequence of the corresponding cohomology groups. There's just a minor drawback of that I can only define like the one co-cycles for this. And because of this first one, the first one here in this sequence is abelian, and that allows me to also define the two co-cycles for this thing. But then it stops, right? So this sequence here stops here, and it's also just a sequence of pointed sets, meaning that each of these, I mean, this is a group, this is fine, but all of these are just pointed sets. And what I mean by exactness is if you take the base point here and take the pre-image of that in here, then that will be the same as the image of this thing here. So that's what replaces the kernel image condition from exactness. Right, but then you get this map at the very end. And this was the thing that characterized G-kernels. And if you work out what this is exactly the third cohomology group with coefficients in the center of the unitary group. And it turns out that this map that you see there will exactly be the lifting obstruction. Right. All right, so there's another one. So if I go back to the assumptions that Izumi made to get his invariant, so U of A is connected, center is the circle, and I have this isomorphism with the fundamental group and the K0 group. Then I get another short exact sequence of cross modules where I now take the universal cover of the unitary group, map that down all the way to the projective unitary group, and then the kernel of that is this modified K0 group, K0 hash. And then the exact sequence of cross modules gives rise to this long exact sequence that stops at this point, and this obstruction that I see at the end is again just Izumi's invariant. All right, there's another obstruction that also works, and that's related to the case where you have a trace state on your C-star algebra. So if you assume that you have a tracial state on the unital C-star algebra, then you can define like the C-star algebraic analog of the special unitary group. Right, so what's the special unitary group? It's generated by the traceless self-adjoint matrices by plugging them into the exponential map. So that's this upper definition here. And then what we show is that actually under these assumptions, or a slightly weaker assumption that the pi1 map, the map on pi1 from pi1 of U of A to K0, if that is surjective, these are actually also the unitaries in the identity component of the unitary group that have determinant 1, if you like. So there's a determinant map if you have a trace, the de la Arp Scarnalis determinant, And this sort of gives you the ones of determinant 1, and that's your special unitary group. And if you have all of the assumptions that Izumi had, so U of A connected, centers the circle, and you have this isomorphism, plus one additional thing, namely that K0 of A injects into the real numbers via the trace, then this special unitary group behaves even more like the special unitary group that you know and love from the finite dimensional case. So in particular, it will be simply connected. If you take the universal cover, then you get special unit, if you take the universal cover of the unitary group, then that will be homeomorphic to the special unitary group times the real line. And you have a short exact sequence, which tells you that the kernel of the projection from the special unitary group to the projective unitary group is this group that's generated by the subgroup of the circle that you get from applying the trace map to K0. Okay, but that gives you another short exact sequence of cross modules, so you get another invariant. So you get a tracial lifting obstruction from this, and you can actually relate the two using this second statement here, right? So we had one cross module coming from the universal cover of the unitary group, which is now homeomorphic in this case to this. So I can relate the two exact sequences, and one can recover results that were known before from this. So for example, this universal cover lifting obstruction, if I go through this homeomorphism there, will split up into a part that comes from the tracial lifting obstruction, but the part that comes from the real line will actually vanish. Right. Okay. So I think, this is kind of a unifying framework for these all of these lifting obstructions. But so far, we can compare them now, fine. So is there more that we can do using this? And now I think I have to confess that I've lured all of you into a trap, because we were doing category theory all along. One thing that I can do when I have one of those topological cross modules is I can construct from this topological 2 category. And here's roughly how this works. So the topological 2 category will have a single object, which I will denote by this little star. Then I have a space of 1 morphisms given by gamma 0. And then I have a space of 2 morphisms as well, which is gamma 0 times gamma 1. And I have lots of compositions here, right? So one composition, I want to think of can I use the mouse? Oh, perfect. I want to think of this pair, alpha u, as a 2 morphism from the 1 morphism alpha to this composition here. And that's what you can see here in these pictures. And now I can compose the 2 morphisms, and that's just the multiplication in gamma 1. So that's this first picture here. So if I have u2 first and then u1, then I just multiply them. But because this is a 2 category, I have another multiplication. Namely, I can compose 2 1 morphisms. And if I have 2 morphisms between the 1 morphisms, then I get this horizontal composition as well. And that's how this works. So this is not the multiplication of u and v, but because I have sort of the alpha here in between, I define this to be u times alpha of v, where I'm now using the action of gamma 0 on gamma 1. And if you write down all of the conditions that you want for these compositions, for example, you want them to be associative, then you find out that actually the rules that you have given for the topological cross modules are designed in such a way that this works. So why am I telling you all of this? Because what turns out to be the case is that these topological 2 categories that you get from these cross modules, they have classifying spaces. So I can take a topological cross module, construct this 2 category from it, and then from the 2 category, I can construct a topological space. And this is constructed from the so-called Daskin-Nerf right? So the Duskin nerve gives you a simplicial space, then you take the geometric realization. This is kind of standard in the world of algebraic topology to get to classifying spaces. But at the end of the day, this is a space that you can associate to each cross module. And the upshot is that if I have one of these one co-cycles for a cross module, then this induces a pseudo-functor from the group to the cross module. So what's a pseudo-functor? Usually a functor would preserve composition. That's one of the rules. But a pseudo-functor doesn't do that because we're ending up in a two category here. And by the way, I'm considering G here as the category also with one object and with G as the morphisms. This will only preserve composition up to some two morphism in G. Right? And then you have conditions that assure that this is compatible. And then this construction here is functorial for these pseudo-functors. So I get now a map, a continuous map between these topological spaces. And what that allows us to do is it allows us to map the cohomology sets that we had here on G with coefficients in the cross module to homotopy sets. Right? So I have this natural transformation from this cohomology set to the set of homotopy classes of maps between BG and the classifying space of the cross module. And you have to check here, of course, that if you change such a co-cycle up to a coboundary, this thing that you had here only changes up to homotopy. But that's something that is true. And now, of course, you want to find out how good are these maps, right? So, I mean, this, if you're unlucky, this could just be the map that sends everything to just one homotopy class, and then you would be none the wiser. So, but there's good evidence that this is something that might be successful. So here's a theorem. Oh yeah, this slide is a bit of a mess, my apologies. So I want you to look at the theorem first, right? So if I take one of those strongly self-absorbing algebras, and I also want it to be a Kirchberg algebra, I want G to be countable, discrete, and amenable, and I also want that BG has a finite CW complex structure. Then I can look at the outer co-cycle actions of G on D up to co-cycle conjugacy, and it turns out that these are in one-to-one correspondence with the homotopy classes of maps similar to the ones that we have seen before. This is the classifying space, and now it's the ordinary classifying space of the automorphism group, where you pick the identity component of the algebra D tensor K, so you have stabilized things. And the way the map from the left to the right works is a bit of a trick. So you can stabilize your action. So if you start with one of those co-cycle actions, then the first thing that you can do is instead of the alpha, you consider alpha tensor the identity. And then you can find a unitary such that if you conjugate by that unitary on the stabilization, this turns the co-cycle action that you had before into an honest action on D tensor K. And once you have an honest action on D tensor K, you can form the associated principal bundle over the classifying space. And these things, the principal bundle, that's exactly what's classified by this cohomology set here. So that gives you from the outer co-cycle actions a homotopy class of maps like this. Right. So how's this related to this thing here? And this is the part where, so this is not published yet, but I think we have a proof now that there's a weak homotopy equivalence between this classifying space that I can associate to this cross module that classified co-cycle actions and B out 0 of D tensor K. And then, of course, the thing left to do is to check that actually this map that we have here corresponds to this stabilization thing that happens here. The nice thing about this is that this allows us to understand the homotopy type of this thing But the procedures work for the other cross modules associated to C-star algebras as well. So you might hope that also the other ones that gave you the lifting obstructions can be understood in this way. And another thing that is great about this is actually if you pick one of those strongly self-absorbing C-star algebras, these homotopy sets that you get turn out to be groups. So that's the result that is now a few years old that I obtained together with Mario Stadelat. So if you have a space X and the classifying space B out 0 D tensor K, then this classifies algebra bundles over your space with fiber D tensor K, and that has a monoid structure with respect to the fiber-wise tensor product, but this monoid structure actually turns out to be a group structure, and we can even determine like which groups you get because we can identify these with something that's known in algebraic topology. Right. I think this is almost everything I have to say. I just wanted to finish with one more thing. So this is a little advertisement for the thing that I've done together with my PhD student Valerio Bianchi. So what we looked at is we looked at this result here and asked ourselves, so what happens if the D itself comes already equipped with a group action? Can we then somehow, I mean, this is the first group in some cohomology theory. Can we somehow relate this to equivariant cohomology? And that actually works quite well. So we looked at G equal to Z mod PZ, so a finite cyclic group of a prime order P. Then we looked at finite dimensional unitary G representations, V, and took the associated UHF algebra. That's the G C-star algebra. Likewise, you can equip the compact operators with like the universal G action. And then if you do that, you can look at the Z mod PZ equivariant C-star algebra bundles over X. And then the result from before is still true. They still form a group. And actually, this group is the first group of an equivariant cohomology theory. And again, we can identify this in terms of algebraic topology. And we've done this for Z mod PZ, but that was mostly because there everything is very concrete and we could compute everything on the nose. But we think that the approach that we have also works for much more general classes of groups and actions. And that's everything to say. So finish here. Thank you.
Any questions?
So can you use this to find anomalous actions on sort of nice class of C-star algebras?
Yeah, that's what I'm hoping for. So I think at least in the case of Kirchberg algebras, one should be able to understand like the homotopy theoretic picture, so maybe this has a chance of being understood. And then of course, because of this result, if you have this and understand maybe the homotopy type of the thing that classify G-kernels, then you might be able to go back here. That's of course a classification type result. So you would have to somehow generalize that.
Is the map from right to left kind of explicit, or?
I don't think it is. This is
Abstract nonsense.
Yeah.
What about doing something like this for fusion categories rather than
Yeah. Yeah, so I can say a few things about that. So these cross modules that I've written down, right? So this U of A maps to out of A. This is like a slice of the two category that you get from just fixing your C-star algebra, that's your object, and then you look at the self-Morita equivalences of that C-star algebra, and then at the intertwiners, or the isomorphisms, the bimodule isomorphisms between these. And because I can associate, now I always get this wrong, one of the two sides. So if I have an alpha in here, I can take A as an AA bimodule, and twist the action by the alpha on one side. And if you do this correctly, it's compatible with composition. Right, so if you do that, then you get the bimodules from this, and then these will just be like the way the two morphisms worked was it went from alpha to essentially at you composed with alpha, right? So, but that's the bimodule isomorphism here. So we are picking slices of the category of like self-Morita equivalences of a C-star algebra. And I think, I mean, that's maybe the even more natural setting to consider, and that's a tensor category. And then, I mean, it's not such a big step to just consider like more general tensor categories, and also to consider actions of more general tensor categories on these C-star algebras. And yeah, so that's where this probably fits together.
Okay, so no more questions. Let's